Imagine a chunk of rock smaller than a mountain quietly overturning decades of assumptions about how our solar system came together. And imagine NASA stumbling onto that discovery almost by accident during what was meant to be a simple systems check. That's essentially what happened with the Lucy spacecraft. And the story behind it is one of the more unexpected chapters in modern space exploration. Lucy lifted off from Cape Canaveral on October 16th, 2021, on a mission that has no real precedent. Its name honors a 3.2-million-year-old human ancestor skeleton unearthed in Ethiopia in 1974, a discovery that reshaped scientists' picture of human evolution. NASA's hope was that this probe could do something comparable for the story of planetary formation. The underlying logic is straightforward. Asteroids are essentially frozen relics. Many have gone largely untouched since the solar system's chaotic infancy, when planets were still forming out of swirling dust and rubble. Examining them closely is a bit like reading an unedited record of how everything around us first took shape. What makes Lucy's mission so ambitious is its itinerary. Over roughly a 12-year span, the spacecraft is set to visit 11 separate asteroids while traveling close to 4 billion miles. More asteroid encounters than any single spacecraft has ever attempted. Its headline destinations are the Jupiter Trojans, two vast clusters of asteroids trapped in Jupiter's gravitational grip, one group ahead of the planet in its orbit and one trailing behind. These objects have never been visited by any spacecraft, and researchers believe they're essentially untouched leftovers from the outer solar system's earliest days. Before reaching those primary targets, though, Lucy had two minor pit stops scheduled. Neither was expected to matter much. Both ended up producing science nobody saw coming. The first stop involved a small asteroid named Dinkinesh, which wasn't even part of the original mission plan. It got added later, once engineers realized Lucy's trajectory would pass close enough for a good look. The plan was simple. Use the encounter purely as a dress rehearsal, a way to test the spacecraft's tracking and imaging hardware ahead of the real target still years away. Dinkinesh seemed like an ideal low-risk choice. Under a mile wide, tucked away in the main asteroid belt between Mars and Jupiter, with nothing about it suggesting anything special. On November 1st, 2023, Lucy zipped past Dinkinesh from a distance of roughly 270 miles. The whole encounter lasted only minutes given the spacecraft's speed. Back on Earth, mission scientists were bracing themselves for nothing more than confirmation that the cameras and tracking systems performed as designed. What arrived instead was one of the more jaw-dropping images in recent planetary science history. Dinkinesh wasn't traveling alone. Circling the small asteroid was a satellite that no telescope on Earth had ever managed to detect. The team named it Selim, an Amharic word for peace, a fitting companion to Dinkinesh, whose name translates roughly to the Marvelous One, with both names tracing back to the original Lucy fossil and its own Amharic name. Discovering a moon around such a modest asteroid was already a nice surprise. Binary asteroid systems exist, but they're uncommon. Catching one during a mission segment billed as a mere calibration exercise made it even more unlikely. And then things got stranger. When researchers took a closer look at the images of Selim, they discovered their initial interpretation had missed something important. What appeared to be a single small companion was, in fact, two distinct rocky bodies, loosely stuck together and orbiting Dinkinesh as if they were one object. Astronomers call this a contact binary. A pairing formed when two bodies drift together so gently that, instead of shattering on contact, they simply merge, much like pressing together two balls of soft clay. This marked the first confirmed instance of a contact binary functioning as a moon orbiting another asteroid, something that had never been documented anywhere in the history of space exploration. Consider how many objects humanity has already flown past: the Moon, Mars, Jupiter, Saturn, Uranus, Neptune, various comets, and dozens of individual asteroids. Not one of those encounters had ever revealed a fused double-body satellite circling another asteroid. Lucy found one on its very first flyby during what was supposed to be nothing more than a warm-up exercise. The plot thickened once scientists examined Dinkinesh itself in detail. They noticed two distinctive surface markings, a long groove running along one side, resembling a deep scar, and a raised band circling the asteroid's midsection, like a belt of accumulated debris. Together, these clues painted a picture of what likely occurred. At some point, Dinkinesh began rotating faster than its structure could handle. The probable culprit is a mechanism called the Y-ARP effect, short for Yarkovsky-O'Keefe-Radzievsky-Paddock, a gradual process in which uneven sunlight striking an asteroid's surface slowly alters its spin rate over long stretches of time, like an invisible force patiently accelerating atop. As Dinkinesh's spin increased, roughly a quarter of its total mass eventually tore free. That fracture created the groove. Some of the ejected material fell back and built up the ridge, while other debris drifted into orbit around the asteroid. Over time, that orbiting material clumped into two separate chunks, which eventually came close enough together to merge into what we now call Selum. In short, a single small asteroid essentially spun itself apart and then, from its own scattered debris, quietly assembled a tiny companion moon system. This research was published in the journal Nature in May 2024 and quickly drew significant interest from the planetary science community. Contributing institutions included the University of Maryland, the Southwest Research Institute, Johns Hopkins Applied Physics Laboratory, and NASA Goddard. The conclusion was unmistakable. Even the least remarkable, seemingly forgettable asteroids can carry surprisingly complex histories, and Lucy stumbled onto one of those histories during what was essentially a test flight. Had this been the mission's only surprise, it would already stand out as a notable achievement. But Lucy had one more early flyby on the schedule, and what turned up there was even harder for scientists to make sense of. The next target was an asteroid called Donald Johanson, named for the paleoanthropologist who helped uncover the original Lucy fossil decades ago. There's a nice bit of symmetry there. A spacecraft carrying the fossil's name, paying a visit to a rock carrying the discoverer's name. But nothing about that connection prepared scientists for what the flyby actually revealed. On April 20th, 2025. Easter Sunday. Lucy passed within roughly 960 kilometers, or about 600 miles, of Donald Johanson, traveling at close to 30,000 miles per hour. The window for observation was so narrow, and the spacecraft moving so quickly, that its instruments had to shut down automatically about 40 seconds before the moment of closest approach, simply to shield the cameras from direct sunlight exposure. Even with that limitation, the data collected over the following days proved remarkably detailed, and it forced a rewrite of what scientists thought they understood about this object. Start with its shape. Earlier ground-based observations had already picked up on periodic brightness changes occurring roughly every 10 days, hinting that the asteroid was elongated and tumbling. Researchers anticipated something irregular and stretched out. What they actually found went beyond that. Donald Johanson turned out to be another contact binary, similar in principle to Selum, two separate chunks that had drifted together and fused. But the connection between the two lobes was unlike anything documented before. NASA's official description likened it to two ice cream cones pressed together tip to tip, forming an unusually narrow, pinched bridge between the halves. The full object measures about 8.8 kilometers in length and roughly 4.4 kilometers across, nearly the length of 100 football fields placed end to end. Scientists estimate this object took shape around 155 million years ago, following a violent collision that destroyed a much larger parent body. Rather than crashing together, the two resulting fragments slowly drifted back into contact under their own mutual gravity and merged gently, described more as a slow, quiet reunion between fragments of the same shattered object than any kind of impact. Researchers from the Southwest Research Institute noted the surface geology is unusually intricate, marked by craters of varying ages and diverse textures reflecting a long, layered impact history. The shape alone would have been remarkable enough, but the rotation pattern proved even more baffling. Telescopes on Earth had already measured a rotation period of about 10.5 days. Unremarkable for an asteroid. What Lucy's close-range data revealed, though, was that this 10.5-day cycle told only part of the story. The asteroid is simultaneously undergoing a separate, independent wobble around its long axis, one that repeats roughly every 26.5 days. Put together, these two overlapping motions mean Donald Johanson isn't spinning smoothly like a ball or a top. It's tumbling erratically through space, more like a badly thrown football than a well-behaved rotating body. Researchers refer to this as a non-principal axis rotation state, and it's genuinely rare. Most asteroids eventually settle into a single stable spin over time. This one hasn't, and its behavior doesn't line up with what existing models had predicted. These results were formally published in the journal Science on June 18, 2026, in research led by Dr. Simone Marchi, Deputy Principal Investigator of the Lucy mission. The paper outlined three standout findings from the Donald Johanson flyby: the unusual double-axis tumbling motion, the striking ice cream cone shape linking the two lobes, and a third result that turned out to be the most remarkable: chemical evidence pointing to liquid water once present inside the asteroid. Lucy carries an onboard infrared spectrometer, and when researchers aimed it at Donald Johanson's surface during the flyby, it picked up a very specific signal: iron-rich clay minerals. Clay doesn't simply appear from dry rock sitting untouched in space. It forms specifically when liquid water interacts with rocky material over an extended period. Finding iron-rich clay on a body this modest in size, under a mile across and only around 155 million years old, implies that at some point in the history of its parent object, actual liquid water was present. Not frozen ice, not vapor. Liquid water inside a rocky body orbiting within the main asteroid belt between Mars and Jupiter. This detail matters because the origin of Earth's oceans remains one of the biggest unresolved puzzles in planetary science. Earth formed too close to the Sun in conditions far too hot for water to have condensed and stuck around during the planet's initial assembly. So the prevailing theory holds that water arrived afterward, carried in by asteroids and comets from cooler, more distant reaches of the solar system that eventually collided with the young Earth. The chemical fingerprint of Earth's oceans reasonably matches what scientists would expect from certain water-bearing asteroid types. Now, Lucy has produced direct chemical evidence of past water activity on a main belt asteroid, showing that water-rich material was indeed active in a region close enough to Earth's neighborhood to have plausibly contributed to our planet's oceans. Scientists compared these clay signatures with results from earlier missions. NASA's OSIRIS-REx mission to the asteroid Bennu and Japan's Hayabusa 2 mission to Ryugu both detected clay minerals of their own. But those clays were magnesium-rich rather than iron-rich, indicating liquid water likely persisted on their parent bodies for a much longer stretch, potentially spanning millions of years, while still embedded within larger objects. The iron-rich composition found at Donald Johanson instead points to a far shorter episode of water activity, a brief chemical window inside its parent body, occurring shortly before that parent was destroyed in the collision that ultimately produced Donald Johanson. Given that Donald Johanson is remarkably young by asteroid standards, roughly 155 million years old, compared to the 1 to 2 billion year age of Bennu and Ryugu. It may represent an entirely separate chapter in how water circulated through the early solar system. These distinctions suggest the parent bodies behind Bennu, Ryugu, and Donald Johanson likely formed in different places and at different times before eventually settling into the main asteroid belt. Each object seems to hold a different piece of the same larger puzzle. Take a moment to consider what's unfolded so far. Lucy has completed just 2 flybys, both officially labeled as warm-up exercises, and both produced discoveries that were, in their respective categories, entirely unprecedented. A fused double-body satellite and a wobbling, 2-lobed asteroid bearing traces of ancient water chemistry. These were merely the opening stops. The mission's true centerpiece, the Jupiter Trojans, is still ahead. Lucy is expected to arrive at the Jupiter Trojan asteroid swarms starting in 2027, and at this stage, nearly everything about what it'll encounter there remains a genuine unknown. No spacecraft has ever visited a Jupiter Trojan before now. Researchers have constructed theoretical models predicting what these objects might be composed of and how they might look. But as Lucy has already shown twice with targets considered minor, models rarely capture the full picture once you actually get up close. The Trojans are believed to rank among the most primitive, least disturbed bodies remaining anywhere in the solar system. Darker in appearance, carbon-heavy, and potentially carrying organic compounds that predate Earth's very formation. Some researchers suspect these objects originally formed far beyond Neptune, out in the solar system's outer fringes, before being gravitationally pulled into Jupiter's orbital region during an early period of large-scale planetary rearrangement billions of years ago. If that theory proves accurate, the Trojans would effectively be carrying material from the most remote, oldest corners of our cosmic surroundings. Lucy is scheduled to visit at least 6 of these objects between 2027 and 2033. Among the targets are members of the Eurybates family, a group of asteroids thought to share a single fractured parent body, along with Patroclus and Menoetius, an uncommon pair of near-identical mass asteroids orbiting one another. Each destination is expected to reveal a different fragment of the early solar system's story, and given how much Lucy has already uncovered at its supposedly unimportant early stops, the scientific community is watching with heightened anticipation. Dr. Hal Levison of the Southwest Research Institute in Boulder, Colorado, leads the mission as principal investigator. Following the Donald Johanson flyby, he noted that the warm-up asteroids were proving to be quite interesting in their own right, a remark that, in retrospect, ranks among the great scientific understatements of recent years. These targets weren't expected to carry much significance. Instead, both delivered discoveries likely to be referenced in research papers for years to come. There's a broader point worth reflecting on here. We're living through a period of space exploration more advanced, better funded, and more technically capable than at any earlier point in history. Spacecraft have grown smaller and more efficient, instruments more sensitive, and the computing power behind data processing far exceeds anything available during earlier decades of space travel. And yet, time and again, whenever humanity actually sends a probe somewhere and takes a close look, the universe proves more surprising than anticipated. Not in small, incremental ways, but in fundamental ones. Objects presumed simple turn out to be complex. Things expected to be dull turn out to be some of the most compelling finds in years. What Lucy uncovered at Dinkiness shouldn't, by conventional reasoning, exist. A fused double moon that came into being because an asteroid spun itself apart under nothing more than the steady, cumulative push of sunlight. What it found at Donald Johanson is equally hard to explain. A two-lobed, ice cream cone-shaped object tumbling on two axes simultaneously, carrying the chemical trace of liquid water that briefly existed roughly 155 million years ago, inside a belt of leftover debris drifting between two planets. And both of these discoveries emerged from targets the mission had essentially treated as an afterthought. The primary destinations remain ahead.